All right, let's take a look at the practice test. For the instructions, we're asked to simplify. We want to write your answer in rectangular form. Before we look at the first problem, I want to revisit something we talked about in the lesson. So we did derive this formula. If you're curious about where it comes from, you can just revisit the lesson. So this guy right here, let's say that we have a complex number in what we call polar form, or some books call this the trigonometric form. So we have r, which is the absolute value or the modulus of the complex number, times the quantity. You have the cosine of theta plus I times the sine of theta. So theta, again, is called the argument. If you think about the complex number as a position vector in your complex plane, again, you can think about theta as the direction angle. So this whole thing is raised to the power of n. So to quickly do this, all you really have to set up is this r raised to the power of n times the quantity. You're going to have the cosine of n times theta plus I times the sine of n times theta. So this n right here is going to be your exponent here, and it's going to be multiplied by your argument here and also here. So that's all you really have to do. All right, let's take a look at the first problem. So here we're going to have 5 times the quantity cosine of 330 degrees plus I times the sine of 330 degrees. And this number is raised to the fourth power. So again, to do this quickly, you're going to take that absolute value, that 5, which is your r value, and you're going to raise it to this power. So 5 to the fourth power. Then times the quantity. You're going to have the cosine of that angle, so 330 degrees, and you're going to multiply by that, so times 4, then plus I times the sine of 330 degrees, and again, you're going to multiply that by 4 and just close that down. So let's say this is equal to 5 to the fourth power is 625, and then times the quantity. For 330 degrees times 4, that's going to be 1,320 degrees. So let's say this is the cosine of 1,320 degrees, and then plus I times the sine of 1,320 degrees. We were asked to write this in rectangular form, otherwise known as the standard form for a complex number, which is a plus bi, or some books will say x plus yi. So what I would first do is find the coterminal angle. So I'm going to include 0 degrees and exclude 360 degrees, but somewhere in that range is where I want to be. So what I would do is say, this guy right here, one complete rotation is 360 degrees. Well, if I multiply it by 2, that's 720 degrees. That's not enough. If I multiplied it by 3, I would get 1,080 degrees. If I multiplied it by 4, I would get 1,440 degrees. Now that's over, so I want to stop with 3. Okay, so this is what I want. 360 degrees times 3 would be 1,080 degrees. And I'm going to subtract this away from 1,320 degrees. That's going to give me my coterminal angle. So let me get rid of this and punch this into the calculator, and that's going to give me 240 degrees. So that's my coterminal angle. So let's get rid of this, and let's say this is 625 times the cosine of 240 degrees plus I times the sine of 240 degrees. Okay, to put this in rectangular form, you need to figure out what is the cosine of 240 degrees, and then what is the sine of 240 degrees, and then you're going to use your distributive property. So for the cosine of 240 degrees and the sine of 240 degrees, in each case, for 240 degrees, you're in quadrant 3. And we know that cosine is negative in quadrant 3 and sine is negative in quadrant 3. And we know that a 240 degree angle is going to have a 60 degree reference angle. So what is the cosine of 60 degrees? Well, it's a half. But we're negative in quadrant 3, so it's negative 1/2 for the cosine of 240 degrees. What is the sine of 60 degrees? Well, it's square root of 3 over 2. But again, we're negative in quadrant 3, so it's going to be the negative of the square root of 3 over 2. So we can just replace this. So let's say this equals 625 times the quantity. For the cosine of 240 degrees, I'm just going to put in negative 1/2. And then over here, I'm going to have a negative, so let me put minus, and then square root of 3 over 2. That's me replacing the sine of 240 degrees with a negative square root of 3 over 2, and then times I. So you can do that there, or you can put it here if you want. Really doesn't matter. So let's put equals here. I'm now just going to distribute the 625 to each guy inside the parentheses. So 625 times negative 1/2 is just negative 625 over 2. And then basically you have minus 625 times square root of 3. So 625 times square root of 3. And this would be over 2. You could put the I here, or again, you can write it here if you want. Let me slide this down. A lot of people will do it like this. So this is your A plus BI format, your rectangular form. So you have negative 625 over 2 minus 625I times square root of 3 over 2. All right, for problem 2, now we have this 2 times the quantity cosine of 60 degrees plus I times the sine of 60 degrees, and this number is being squared. So again, to use the formula, you're going to square this absolute value or modulus here. So 2 is being squared, and then times the quantity, the cosine of, again, this angle here is being multiplied by this 2 right here. So this would be 2 times 60 degrees plus I times the sine of, again, it's going to be 2 times 60 degrees. Let me close that down. So this would be equal to 2 squared we know is 4, and then times the quantity, the cosine of 2 times 60 degrees is 120 degrees. So let's put 120 degrees here, and then plus I times the sine of, again, this would be 120 degrees. Now we're asked to put this in rectangular form or the standard form, the a plus bi, or again, the x plus yi. So what is the cosine of 120 degrees? So just like in the last problem, we have a reference angle of 60 degrees. Let me put sine of 120 degrees here as well. So we're in quadrant 2, so cosine is negative and sine is positive. So just think about 60 degrees, the reference angle. The cosine of 60 degrees is a half. So because we're in quadrant 2, this would be negative 1/2 for the cosine of 120 degrees. Now the sine of 60 degrees is square root of 3 over 2. Now 120 degrees is in quadrant 2, so we just keep that. So it's just the square root of 3 over 2. And let's say that this is equal to 4 times the quantity. This for the cosine of 120 degrees, again, that's just negative 1/2. So this is negative 1/2. And then we're going to replace the sine of 120 degrees with square root of 3 over 2. So let's go plus square root of 3 over 2. So then times I, you can put it like that, or you can put it there. Again, whatever you want to do. So let's say this equals, I'm going to distribute this 4 to each guy here. So you'd have 4 times negative 1/2 plus 4 times square root of 3 over 2 times I. So for the final answer here, the 4 would cancel with the 2 and give me a 2. So this is going to be 2 times negative 1 or negative 2. And then plus the 4 would cancel with the 2 and give me a 2. So this is going to be 2 times square root of 3 times I. Or again, you could just put the I here. So let's put the 2I times square root of 3 like that. So in my rectangular form or standard form, you get negative 2 plus 2I times square root of 3. Or again, you could say negative 2 plus 2 times square root of 3 and then times I. All right, for the next few problems, the instructions are going to change. We're asked to simplify, write your answer in polar form. So looking at problem 3, now we have our complex number given in rectangular form or the standard form, again, the a plus bi. So negative 5 times square root of 2 over 2 plus 5 times square root of 2 over 2 times the imaginary unit I. This number is cubed or raised to the third power. So let's put that this equals, I'm going to first convert it over into the polar form. That way I can use my formula. So let's go ahead and say that this is going to be some r value times the quantity cosine of theta plus I times the sine of theta. And then this guy right here is going to be cubed. Okay, let's start out by finding the r value. Again, that's the absolute value of the complex number. So we'll say that r is equal to the principal square root of, you want this guy squared plus this guy squared. So in other words, the real part, which is negative 5 times square root of 2 over 2 being squared, then plus this guy right here, the imaginary part, so 5 times square root of 2 over 2 being squared. Now, when we think about these guys, this guy and this guy, when you square them, they're going to be the same, right? The only difference between the two is that this one's negative and this one's positive, but that negative is inside the parentheses, so it's basically going to go away. So if I square the negative, it goes away. If I square 5, I get 25. If I square the square root of 2, I get 2. And if I square 2, I get 4. Now I can cancel a common factor of 2 between numerator and denominator, so this gives me 25 over 2, and I'm going to get the same thing over here. So this is 25 over 2 plus 25 over 2. So you can add 25 plus 25, that's 50, over the common denominator of 2. And we know that 50 divided by 2 would be 25, and then the principal square root of 25 is going to be 5. So this r value here, or the absolute value of the complex number, is going to be 5. In terms of theta, again, the argument, it satisfies the tangent of theta is equal to the b over the a, or you could say y over x, or imaginary over real. So I'm going to say that the tangent of theta is equal to, let's take the imaginary part, so 5 times square root of 2 over 2, and then divide that by the real part. again, because I'm dividing with fractions, I'm going to multiply by the reciprocal. So the negative of 2 over 5 times square root of 2. So we know by looking at this that this is going to be negative 1 because the only difference between these two numbers is going to be the negative sign there. So let me go through and cancel this. So this would cancel with this, and this would cancel with this, and I'm just left with negative 1. Okay, let me put a 1 there. So this is negative 1, and you can actually just erase this. Now, before we use our inverse tangent function, let's think about this for a moment, right? We could sketch this if we wanted to, but I think we really don't have to at this point. We know that from the origin, because the real part is negative, I'm going to go to the left, and then I'm going to go up because the imaginary part is positive. So from the origin, if I go to the left and then I go up, I'm going to be in quadrant 2. So I know that that's why this guy is negative, right? Because tangent values are going to be negative in quadrants 2 and 4. If I use my inverse tangent function with negative 1 as the argument, we all know we're going to get negative 45 degrees. So because that puts me in quadrant 4, rotating clockwise, I have to swing myself around 180 degrees to get to where I want to go. So for theta, I would have to say it's negative 45 degrees plus 180 degrees. So that would give me 135 degrees. Now that's one way to do it. And some people don't like that method. I think that's probably best if you're drawing a sketch, and we didn't do that here. So what you can do if you want to do this without a sketch, you can just erase this and say, okay, well, I'm just going to take the absolute value of this. So the tangent inverse of positive 1 will give me 45 degrees. So that would just be my reference angle in quadrant 2, right? So going to quadrant 2, you'd say 180 degrees minus 45 degrees. That will give you that same 135 degrees. So two different ways to think about it. Okay, let's get rid of this and get rid of this. And we know that's 135 degrees. This right here is 135 degrees. And this right here, let me scooch this down, is also 135 degrees. Okay, let's put equals here. And now we can just find our answer. So this 5 right here is going to be cubed. We know that's 125. I'll replace that in a moment. So this right here would be the cosine of 3 times 135 degrees plus I times the sine of 3 times 135 degrees. Let me close that down. Let's put equals. So we know that 5 cubed is 125. And then times, you have the cosine of 3 times 135 degrees. That's going to be 405 degrees. Then plus I times the sine of 405 degrees. Now, I would not leave it like this, although a lot of teachers will allow it. I always like to find the coterminal angle that's between 0 degrees and 360 degrees, where 0 degrees is included and 360 degrees is not. So for this one, it's real easy. Just take 405 degrees and subtract 360 degrees away, and that's going to give you 45 degrees. So let's say this equals 125 times the quantity cosine of 45 degrees plus I times the sine of 45 degrees. And if you want to work with radians, remember 45 degrees is pi over 4 radians. So you could also say this is 125 times the quantity of the cosine of pi over 4 plus I times the sine of pi over 4. All right, let's take a look at problem 4 now. So once again, we're given the complex number in the rectangular form, or again, you can call this standard form, the a plus bi, or the x plus yi. So we have the negative of 3 times square root of 2 over 2, minus 3 times square root of 2 over 2 times I, and then this number is raised to the 5th power. Okay, let me put equals here, and let's drop down a bit. We're looking for r times the quantity cosine of theta plus I times the sine of theta, and then this whole thing here is raised to the 5th power. Let me actually slide this down just a little bit for formatting, and let me come down here. So first the r value, again, that's the absolute value of the complex number. So this is the square root of, you take the real part. So this is negative 3 times square root of 2 over 2. And you're going to square that, and then plus. The imaginary part here is exactly the same. So negative 3 times square root of 2 over 2, and that's going to be squared. All right, now before I do anything here, remember, if you had something like, let's say a squared plus a squared again, this is 2a squared. Or again, if you saw x squared plus x squared, this is 2x squared, right? We know this rule. This is this guy squared plus the same thing squared. So it's just like I'm using this. So what I can do to shortcut this a little bit is get rid of that and just say it's 2 times this guy being squared. So squaring this guy if I square the negative, it goes away. 3 squared is 9. Square root of 2 squared is 2. And then 2 squared is 4. So you can cancel a common factor of 2 between numerator and denominator. Let's get rid of this. And this is just times 9 over 2. And we know that the 2's would cancel. So basically, this is just going to be the square root of 9, which is going to be 3. Okay, so that's going to be my R value there. Let me get rid of this. So for theta, it's going to be extremely easy to get because if you think about it, the tangent of theta, again, is imaginary over real, or you could say b over a or y over x, whatever you want to do. This guy right here and this guy right here, it's the same number. So any non-zero number divided by itself is going to give you 1. So I know this is 1, and I think we all know that the inverse tangent of 1 is going to be 45 degrees. Now, I am not in quadrant 1. You can see that this is negative and this is negative. So from the origin, I'm going to the left and I'm going down. So I'm going to be in quadrant 3, and that makes sense because my tangent values are positive in quadrant 3. So what you could do is add 180 degrees to this to swing yourself around, or again, you can just go into quadrant 3 and say, how do I get an angle with a reference angle of 45 degrees? Well, it's actually the same thing. You would take 180 degrees and then add the reference angle of 45 degrees. Either way, you're going to end up with 225 degrees. So let's get rid of this and just say that theta is 225 degrees. And let's put that right there. I'm actually going to slide this down so it fits. So this is 225 degrees. Okay, let's put equals here. And let's slide down. So now I have this 3 that's going to be raised to the 5th power. So let's put 3 to the 5th power. And most of you know that's 243, but we'll replace that in a moment. Then times the quantity, you're going to have the cosine of 225 degrees times 5. So let's put 5 times 225 degrees plus I times the sine of 5 times 225 degrees. Let me close that down. Let's put equals here. 3 to the 5th power, again, that's going to be 243. And then times the quantity, you have the cosine of 5 times 225 degrees. That's going to be 1,125 degrees. So let's say the cosine of 1,125 degrees. Then plus I times the sine of, again, it's the same thing, so 1,125 degrees. Let's close that down. Now, what I would do is put this in terms of its coterminal angle. Again, not required in most situations, but it's just something I'm comfortable with. So if you think about 360 degrees, again, you could multiply it by 2, that's 720 degrees. That's not quite enough. I would multiply this by 3, which would give me 1,080 degrees. And if I do 1,125 degrees minus 1,080 degrees, I'm going to get 45 degrees, or again, pi over 4 in terms of radians. So this would be 243 times the quantity cosine of 45 degrees plus I times the sine of 45 degrees. Or again, you could say this is 243 times the quantity, the cosine of pi over 4 plus I times the sine of pi over 4. All right, for the next problems, the instructions are going to change again. So now we want to find all nth roots, write the answer in polar form. Okay, before we look at the problems, I just want to revisit the formulas that we talked about in the lesson. Again, if you want to know where this stuff comes from, you can just revisit the lesson. So we have the nth root of r times the quantity cosine of alpha plus I times the sine of alpha, where alpha, again, if you're going to use degrees, it's here. If you're going to use radians, it's here. So the only difference is here you have 360 degrees, again, 1 full rotation. Here you have 2 pi, 1 full rotation. So degrees and then radians. But basically for alpha, it's theta divided by n, and then plus 360 degrees times k over n. And then here for alpha, it's theta over n plus 2 pi times k divided by n. Now, when you think about k, again, it's 0, 1, 2, and then you have the 3 dots for the pattern, and then you have the n minus 1. Okay, so what does that mean? Well, essentially, let's say you're trying to find the 4 fourth roots. Well, what you want to do is say that n is 4, so you're going to go to 4 minus 1 or 3, so it's always 1 less. If you're trying to find the 5 fifth roots, well, then you want to go to 4, always 1 less. If you wanted to find the 3 cube roots, well, then you'd want to go to 2, so always 1 less. So let's come down here and look at problem number 5. So we want to find the 3 cube roots of this number. So what you first want to do is put this into polar form. So let's do that real quick. Again, this is r times the quantity, cosine of theta, plus I times the sine of theta. So what is my r? Well, this is the principal square root of, you're going to have 3 halves being squared, plus you're going to have this negative 3 times square root of 3 over 2 being squared. So again, the real part being squared plus the imaginary part being squared underneath that square root symbol. So let's say this is equal to, for this guy, 3 squared is 9, and then 2 squared is 4. So let's say this is the square root of, this is 9 over 4, and then plus, the negative goes away, 3 squared is 9, square root of 3 squared is 3, and then 2 squared is 4. So this is 27 over 4 plus 9 over 4, which is 36 over 4. And we know that 36 divided by 4 is 9, and the principal square root of 9 is going to be 3. So the r value here is just going to be 3. So let's put that there. All right. For theta, let me come back up here so we can see. Again, the tangent of theta is equal to the imaginary, which is negative 3 times square root of 3 over 2, divided by the real. So let me multiply by the reciprocal of 3 halves. So that's going to be 2 thirds. So let's go ahead and cancel this with this and this with this. So that gives me the negative of the square root of 3. Okay, let me get rid of this and do this. So let me use my inverse tangent function. So tangent inverse with the negative of the square root of 3 as the argument. So that's going to give me negative 60 degrees. Now, what does this mean? Remember, for this guy right here, if you were to plot this complex number in the complex plane, the real part is positive and the imaginary part is negative. So from the origin, I'm going to the right and then I'm going down. I know I'm in quadrant 4, but I don't want this negative angle here. So to correct for that, again, I'm just going to add 360 degrees. So I would just say that theta is going to be equal to negative 60 degrees plus 360 degrees, which is 300 degrees. Now, the other way you could have done that, again, this is probably more popular. You just say you want the inverse tangent of the square root of 3. That's going to give you 60 degrees. I know I'm in quadrant 4, so what angle in quadrant 4 has a reference angle of 60 degrees? Well, it's going to be 360 degrees minus 60 degrees or 300 degrees. So either way you want to do it, you end up with 300 degrees for your argument theta. So let's put that in there. So 300 degrees and then 300 degrees. Okay, so now it's just a matter of using our formula, and we can come back real quick and revisit this. Again, here, n is going to be 3. So it's the cube root of whatever r is. In this case, r is 3. So coming back down, we'll say that for the roots, let me put a little border here and put my roots. We're going to have the cube root of 3, and then times the quantity, the cosine of, again, this alpha, plus I times the sine of this alpha. Now, again, to get alpha, we want theta divided by n. Theta is 300 degrees in this case, and n is going to be 3. So 300 degrees divided by 3 would be 100 degrees. So let me put that alpha is going to be equal to 100 degrees. And then you're going to go plus, let me come back. You also have 360 degrees times k. Now, k is going to be 0, 1, and 2, because again, we always go 1 less than whatever n is, and then divided by n. So we're going to start with 360 degrees times 0, which is 0. So forget about dividing by n. It's not going to matter. So let me go down here, and let me start with 100 degrees. So we're going to put 100 degrees there, and then we're going to go 100 degrees there. We're going to take k and then times the 360 degrees divided by your n, which is 3. So 360 degrees divided by 3 would be 120 degrees. So basically, we're just going to keep adding 120 degrees. So when we do 1 times 120 degrees is 120 degrees. And then when we do 2 times 120 degrees is 240 degrees. So let's go ahead and say that we're going to go the cube root of 3 times the quantity cosine of, I'm going to add 120 degrees. So that would give me 220 degrees plus I times the sine of 220 degrees. And then for the last one, we're going to have the cube root of 3 times the quantity cosine of, again, just add 120 degrees to this. That's going to be 340 degrees. So let's put that there, plus I times the sine of 340 degrees. So this would be the 3 cube roots for your complex number. All right, let's take a look at problem number 6. So here we have negative 3 plus 3i times square root of 3, and then n is given to us as 3. So we want to find the 3 cube roots for this number right here. And we will first find the polar form. So let's say that r is equal to the square root of the real part, so -3 squared, plus the imaginary part. This is 3 times square root of 3 being squared. So -3 squared is 9. And then 3 squared is 9. Square root of 3 being squared is 3. So this is 9 times 3 or 27. And then we know that 9 plus 27 is going to be 36. So the square root of 36 is 6. So the r value here is 6. So times the quantity. Cosine of theta plus I times the sine of theta. So for this particular situation, the tangent of theta is equal to what? Again, imaginary over real. So let's go 3 times square root of 3 over -3. And we know that this 3 would cancel with this 3, and you can put this as a -1 down here. And let's say this is the negative of the square root of 3. Okay, let's think about this for a moment. This guy right here, the real part is negative, the imaginary part is positive. So from the origin, I'm going to the left, and then I'm going up. So that puts me in quadrant 2. So you could plug this in as an argument in the inverse tangent function, but you're going to get something in quadrant 4 rotating clockwise. So you're going to have to add 180 degrees to swing yourself around. Or I think a lot of people would prefer to just go inverse tangent of, I'm just going to make this positive, so square root of 3. This would be my reference angle in quadrant 2, right? So let's go into the calculator and key that in. I think maybe a lot of you know that that's going to be 60 degrees. But essentially in quadrant 2, if I have a 60-degree reference angle, well, it's 180 degrees minus 60 degrees, and that's going to give me 120 degrees. So my theta here is 120 degrees. So we want to find the roots here, the 3 cube roots. Let me put a border here like this. So what's our formula? Again, for this guy right here, we would take the nth root of whatever that number is, that r, right? It's the nth root of r like this. So in this case, the n is 3 because we want to find the 3 cube roots. And then the r value is going to be 6. Okay, then we're going to set this up as the cosine of blank plus I times the sine of blank. Okay, so let's put this like this. And let's put this like this. Let's remember that I'm just going to put theta here is 120 degrees because this is going to get cut off. So for the first one, remember, we're doing theta divided by n. So in this case, theta is 120 degrees and n is 3, right? So 120 degrees divided by 3 is going to give you 40 degrees. And then it's plus 360 degrees times k over n, right? So let's come back. So this one is 40 degrees and this one is 40 degrees. And in each situation, you're adding what? Well, it's going to be 360 degrees divided by n, which is 3, so that's 120 degrees, and you're just adding that to the preceding one. So in other words, in this case, 40 degrees plus 120 degrees would be 160 degrees. So this would be 160 degrees, and then you're going to add that again, so 160 degrees plus 120 degrees, that's going to give you 280 degrees. So these are my 3 cube roots for that complex number. All right, let's take a look at problem 7. So for this one, to get a little change up, I'm going to do it in radians. You can also do it in degrees if you want. So we have 5 times square root of 2 over 2 plus 5 times square root of 2 over 2 times I. The n here is 3, so we're looking for the 3 cube roots of this complex number. So again, let's put this into polar form, and this one's real easy to do. So r is equal to the square root of, you're going to go 2 times this quantity 5 times square root of 2 over 2 squared. Again, you could do 5 times square root of 2 over 2 squared plus 5 times square root of 2 over 2 squared under the square root symbol. But again, that just changes over into this form if you want to make it a little bit simpler. So this guy right here, 5 squared is 25, and then times the square root of 2 squared is 2, and then 2 squared is 4. So this is going to be 25 over 2. And so let me get rid of this and say this is 25 over 2 times 2. The 2's would cancel. So this is the square root of 25, which is going to be 5. So let's say that this is 5 times the quantity. The cosine of, I think we can just look at that and tell that that's going to be 45 degrees, or pi over 4 in terms of radians, plus I times the sine of pi over 4. Now, how did I do that so quickly? The same non-zero number divided by itself is 1, right? So we know that if you looked at the tangent of theta, it would be 1, right? So you could say that the inverse tangent here of 1 is 45 degrees, or pi over 4 if you're working with radians. So this guy right here is in quadrant 1, so that's the exact angle we're looking for. Okay, so we're going to adjust our formula again and work with radians here. Let me come down like this. Let me put this like this and just put that we have our roots here. So we want 3 of them. Again, coming back, you probably memorized this at this point. We want the nth root of r times the quantity cosine of alpha plus I times the sine of alpha. Again, for the k, it's going to start at 0, and in this case, go up to 2, right? We want n minus 1, and it's 3, so we're going to go up to 2, 0, 1, and 2. And then down here, for alpha, it's theta, which in our case is pi over 4. So pi over 4 divided by n, which is 3. So you can multiply this by a third. So this is basically going to start with pi over 12, okay? So that's going to be your initial guy. Remember, this 2 pi times k, because k starts at 0, this is just going to go away. So the first one's just going to be pi over 12, right? And then the additional ones, you're going to be adding 2 times whatever k is. So you're going to do 2 times 1 times pi over n is going to be 3. So basically, 2 pi over 3 is what you're going to add the first time. So 2 pi over 3. Let me actually do this now. So you're going to have pi over 12. Then you're going to have pi over 12 plus 2 pi over 3. And then the next one is going to be pi over 12. Plus, you'd have 2 pi times 2 over 3. So 4 pi over 3. Let me come down here. So this would be the cube root of 5. This would be the cube root of 5. And this would be the cube root of 5. You come down here a little bit more. Let me paste that in off to the side here. So this is going to be, for the first one, it's just pi over 12, right? So the cosine of pi over 12, and that's because k starts with 0, okay? So let's put plus I, let me get rid of this, times the sine of pi over 12. So that one's really easy. For the next one, you start with the pi over 12, but now you have to add 2 pi over 3. So I'm basically adding 2 pi over 3, and then I'm adding 2 pi over 3 again. So if we can remember that, let's just get rid of this. If we can remember that, we're starting with this and we're just adding 2 pi over 3, I think we'll be good to go. So pi over 12 plus 2 pi over 3. So let's say this is times 4 over 4. I think this is why people don't like working with radians, because you have to work with fractions. So this becomes 8 pi over 12. And so this becomes 9 pi over 12. Okay, let me get rid of this. And let's say that this is going to be cosine of 9 pi over 12. And then plus I times the sine of 9 pi over 12. Now, you can reduce that because 9 and 12 each have a common factor of 3. 9 divided by 3 is 3, and 12 divided by 3 is 4. So 3 pi over 4. Let's go ahead and reduce that. Okay. Now for this one, again, I'm just going to add 2 pi over 3. So I'm going to take the 3 pi over 4 and add another 2 pi over 3. Again, if you wanted to do it from this one, you can go pi over 12 plus 4 pi over 3, but I think this is a little bit easier just to incrementally do it. So again, it's up to you. So for this one, I'm going to multiply by 4 over 4. And then for this one, I'm going to multiply by 3 over 3. So let's go ahead and say that this is going to be 9 pi over 12. So this is 9 pi over 12. And then plus, this would be 8 pi over 12. So 8 pi over 12. So this would be 17 pi over 12. So let me get rid of this and just say that this right here would be the cosine of 17 pi over 12 plus I times the sine of 17 pi over 12. So this would be your answer in radians. If you want to use degrees, of course, you could have done that. A lot of people find that easier because you don't have to work with fractions. But this would be your 3 cube roots for that complex number. All right, for problem 8, now we have negative 2 times square root of 3 plus 2i. And here we're given that n is 4. So first, again, let's put this in polar form. So r is equal to the square root of. You take this negative 2 times square root of 3. That's going to be squared. Then plus, you take this 2. That's going to be squared. So this equals to, let's say the square root of negative 2 squared is 4. And then times square root of 3 squared is 3. And then plus 2 squared is 4. So we know that 4 times 3 is 12, and 12 plus 4 is going to be 16, and the square root of 16 is going to give me 4. So let's go ahead and say that this right here is going to be 4 times the quantity cosine of theta plus I times the sine of theta. So for theta, we'll say that the tangent of theta is equal to, again, the imaginary, which is 2, over the real, which is negative 2 times square root of 3. So let's cancel this with this. And this is going to end up giving me, let me put a 1 up there, negative, let's go 1 over square root of 3. So this is times square root of 3 over square root of 3 to rationalize the denominator. So this equals, we'll say that this is the negative of the square root of 3 over 3. All right, let me get rid of all this. So I can, again, think about from the origin, I'm going to the left and I'm going up. So I'm going to be in quadrant 2. So however you want to think about this, if you want to go inverse tangent with this guy, the negative of the square root of 3 over 3, again, you're going to get something in quadrant 4 rotating clockwise. So you have to add 180 degrees to that to swing yourself back around into quadrant 2 where you need to be. Alternatively, you can just say inverse tangent of this guy being positive, so square root of 3 over 3. Let me make this a little bit better here for the notation. And this guy right here would give you your reference angle that you're going to need to go into quadrant 2 and work with. So let's key this into the calculator. And if you do it this way, you get negative 30 degrees. If you do it this way, you get positive 30 degrees. So either way, with this one, you add 180 degrees, you get 150 degrees. With this one, you go into quadrant 2 and you say, what angle has a reference angle of 30 degrees? Well, you take 180 degrees, you subtract away 30 degrees, and you get 150 degrees. So let me get rid of this. We'll say theta is 150 degrees. But I think for this example, I wanted to work with radians. I believe that's how it's given in the practice test. So let's say that theta is equal to 150 degrees. Let's convert this over. I think a lot of you know this is 5 pi over 6, but just in case you don't, let's say this is pi over 180 degrees. So let's go ahead and say that immediately we can cancel the degree unit. You can cancel a common factor of 10. So 15, let's write that as 5 times 3. So this is 5 times 3. For 18, let's just write it as 6 times 3. We know we can break it down further, but we don't need to. So this is going to cancel. So let me write 5 pi over 6 here. And let me write that in here and then also in here. And if you want to work with degrees, you can. It's a little bit simpler because you don't have to deal with fractions, but I think some teachers will require you to work with radians. So it's good to get some examples in. Okay, so thinking about our little formula, maybe we can just write it here, that we don't have to go back and forth. And I'll just put right here for my roots. So this would be for the roots. We want the 4 fourth roots. So again, you're going to have the 4th root of 4, and then you're going to have the 4th root of 4, and then you're going to have the 4th root of 4, and this is going to run off. So let me come down here. And then you're going to have the 4th root of 4 again. So let me set this up, and this up, and this up, and this up. And you have the cosine of blank. Let me put that in each case. Okay, so what's the first guy here? Again, if you think about your alpha, the first thing is you take your theta, which in this case, it's 5 pi over 6, and you want to divide that by whatever your n is. So n is 4 here, so let's just multiply by 1/4. So this is going to be 5 pi over 24. So 5 pi over 24. Let's put that in there. Now, when you work with these types of problems, the first one, because k starts out at 0, you've already found this. You don't need to add anything to it because you're adding 0, and adding 0 to something doesn't change anything. So that's the first guy. So plus I times the sine of 5 pi over 24. Okay, close that down. For the next guys, you do need to add something on. So in each case, you're going to start with, let me put a little border here. You're going to start with 5 pi over 24, and then you're going to add, you basically have the 2 pi times whatever k is divided by your n. Okay, so in this case, n is 4. So basically, you could say that this is 1/2. Let me just put times 1/2 over here, times your pi times k. So let me actually just write this as pi over 2, like this, and get rid of this. So it's pi over 2 times whatever k is. So in the first situation, k is going to be 1. Then it's going to be 2. Then it's going to be 3. So what I can do is I can just keep adding pi over 2 to whatever the previous guy is. Or you can go through and key the formula in each time. It's really up to you. But it's just a matter of just adding pi over 2 each time. So let me start out by adding pi over 2. And I'm going to multiply this by 12 over 12 so I can have a common denominator. And so this would be 12 pi over 24. So 12 pi over 24. And so 5 plus 12 is 17. So this is 17 pi over 24. So that's going to be this angle right here. So let me get rid of this and say that this is the cosine of 17 pi over 24 plus I times the sine of 17 pi over 24. Okay. Again, we're just going to add pi over 2. So here, if you had 17 pi over 24 plus, again, I'm just going to add pi over 2, or you can key the formula in each time. Again, that's up to you. This is going to be times 12 over 12. So this would give me 12 pi plus 17 pi, which would be 29 pi over 24. So this would be 29 pi over 24. So plus I times the sine of 29 pi over 24. Let me scooch down a little bit and try to fit this all on here. So this one, again, I'm just going to add pi over 2. So 29 pi over 24 plus, for pi over 2, again, I'm going to multiply by 12 over 12. So this would be 12 pi over 24. 29 plus 12, that's going to be 41. So this would be 41 pi over 24. So this would be 41 pi over 24. So plus I times the sine of 41 pi over 24. Okay, so this would be the 4/4 roots. Again, if you want to work with degrees, it would be a lot easier. I forgot to close down the parentheses there, so just cleaning that up for notation purposes. But this, again, would be the 4/4 roots for that complex number. All right, for the next few problems, the instructions are going to change. We're asked to find and graph all complex solutions in polar form. All right, let's take a look at problem 9. So we have x to the 4th power minus I equals 0. So for this type of problem, really all you have to do is add I to both sides. So we'll say that x to the 4th power is equal to the imaginary unit I. So basically, to solve this equation, I want a number that I can plug in here for x that when I raise it to the 4th power gives me I. Well, what I can do is I can find the 4/4 roots of the imaginary unit I, and then those would be solutions for my equation, right? I could plug them in for x, and if I raise them to the 4th power, I would get I. So let's come down here, and let's think about this. First, I would write I in polar form. So let's just put 1I there to make that crystal clear. And let's also put that this is equal to 0 plus 1I. And so in polar form, the R value is just going to be 1. So we would say that R is equal to the square root of 0 squared is 0, then plus 1 squared is 1. So the square root of 0 plus 1 is the square root of 1, which is 1. Okay, let's put 1, then times your quantity, the cosine of, what's my theta here? Well, for this one, again, if this is 0 and this is 1, just think about this on the coordinate plane. Let me just draw a sample coordinate plane here real quick. And it doesn't have to be perfect, but essentially, this guy is going to be right here. So starting at the origin, I'm just going to go like that. So what is my angle? Well, it's going to be 90 degrees or pi over 2 in terms of radians, right? So essentially, this guy right here, we can work with degrees. Let's just say this is 90 degrees, then plus I times the sine of 90 degrees. And this works because, again, cosine of 90 degrees is 0, sine of 90 degrees is 1. So basically, this is 0 plus 1I times 1, which just puts you back to 1I or just I. Let me get rid of this now. I'm going to keep that 1 there for clarity, just because we need it with our formula. So for the 4/4 roots, again, that's going to be the solution for our equation here. Let me come down here. And we'll just say that we want, again, the formula is the nth root of whatever R is. So it's the 4th root of 1. Well, we know the 4th root of 1 is 1. So we'll just say that this is going to be 1 in each case. So 1 and 1 and 1 and 1. And let me put x equals and x equals and x equals and x equals here, just for clarity. Let me actually make that a little bit better there for formatting. So 1, 1, 1, and 1. And you can drop these in a little while, but I'm just going to put the 1 out there for now. So let me put times the quantity here. So you want the cosine, the cosine, the cosine, and the cosine. So again, the formula, if you're working with degrees, you're going to take your 90 degrees, your theta, and divide it by your n. So what is 90 degrees divided by n is 4 here? Well, that's going to be 22.5. So this is 22.5 degrees plus I times the sine of 22.5 degrees. Remember, for the first one, you don't need to add anything to this because you always start with k being 0, okay? 0 times anything is 0, and if you add 0 to something, it remains unchanged. For the next one, again, if you think about this, you would have, let me put a little border here, 22.5 degrees, then plus, here's where you start with that 360 degrees times k divided by n. Okay, so n is 4. And you can divide this now. So 360 degrees divided by 4, that's going to be 90 degrees. So this is 90 degrees here. And you're basically just multiplying this by k. So all you're doing in each case is just adding 90 degrees to the previous angle measure. Okay, so you don't need to write this out each time. So this guy would start with 1. So let me take 225 degrees, the previous guy here, and add 90 degrees. So that's going to give me 112.5 degrees. So this is 112.5 degrees. So plus I times the sine of 112.5 degrees. And then again, just add 90 degrees again. So that would give me 202.5 degrees. So let me write that in there. And that 5 could be better. Maybe I can make that whole thing better. So 202.5 degrees like that. And then add 90 degrees again. That's going to give me 292.5 degrees. Let's put that in there like that. Okay, now you can get rid of the 1 times. It doesn't make a difference here, so you can just drop the parentheses altogether. So here are the solutions for x. Now, you can convert this over into rectangular form, and that's what you're going to get if you plug this into like an online calculator or something like that. If you said x to the 4th power is equal to I, or x to the 4th power minus I equals 0, you would get the solutions in rectangular form. So you can go ahead and do that on your own if you want, and you'll see that they work. Now, in terms of graphing these guys, we know that we would just set up a little unit circle because the magnitude of each complex number, if you sketch it as a vector, it's going to be 1, right? The R value is 1 in each case. So the tip of each vector here touches that unit circle. Okay, so you see that. And then basically the angles are spaced 90 degrees apart. So the first one here is 22.5 degrees, okay? Then you go 90 degrees to get to the next solution, 112.5 degrees. You go 90 degrees to get to the next solution, 202.5 degrees. And then you go 90 degrees to get to the next solution here, which is 292.5 degrees. And as you keep going around, now you're just repeating your solutions. So this would be the first guy we found. So the SIS is the abbreviation, 22.5 degrees. And then the SIS, 112.5 degrees. And then the SIS, 202.5 degrees. And then lastly, the SIS, 292.5 degrees. Okay, let's take a look at problem 10. So here we have x cubed minus, you have this quantity 4 plus 4i times square root of 3, and this equals 0. So to solve this equation, I'm just going to say that x cubed is equal to, I'm going to add this quantity to both sides, okay? So I'm going to just say that this is going to be 4 plus 4i times square root of 3. If you want to do this the long way, you would distribute the negative to each guy here, and then when you add it to each side, you're going to get right back to this. So that's up to you if this is a little confusing for you. But again, all I'm trying to do here is figure out what can I plug in for x and cube it and get this number here. Well, again, all I have to do is find the 3 cube roots for this number, and I'll find my solutions for x. So let's come down here, and let's begin by finding this guy in polar form. So your r value is equal to the square root of, you have 4 squared, which is 16, plus you have your 4 times square root of 3 being squared. Now 4 squared is 16, and then times square root of 3 squared is 3. So this would be 16 times 3, which is 48. And if you do 16 plus 48, that's going to give you 64, and the square root of 64 is 8. So the r value here is going to be 8. Okay, so then times the quantity, the cosine of theta, plus I times the sine of theta. So let's think about this. We know that the tangent of theta is equal to the imaginary, which is 4 times square root of 3, over the real, which is 4. So that's going to end up giving me, the 4's would cancel, just the square root of 3. So this is the square root of 3. Now this is going to be in quadrant 1, because this is positive and this is positive. So really I can just say that theta is equal to the inverse tangent of the square root of 3. So we know that's going to be 60 degrees. So let me put that in there and put that in there. Okay. So here's where we go through again and just use our formula. Let me slide down here and just say that x is equal to, and we're going to have 3 of these. So then x is equal to, and then x is equal to. You want the cube root of 8, right? So it's the nth root of r. So n is 3, r is 8. Now the cube root of 8 is actually going to be 2. So let's put a 2 here, a 2 here, and a 2 here. Let's set up the parentheses in each case. So for the first guy, again, when you say the cosine of alpha, right? Let me put cosine here and cosine here. This alpha in the first case, just comes because k starts off as being 0. You just take 60 degrees, whatever theta is, and you divide it by n. In this case, that's 3. So 60 degrees divided by 3 would be 20 degrees. So this first one's real easy to get. It's just going to be 20 degrees. So plus I times the sine of 20 degrees. All right, so here's where everybody gets lost. For the next one, again, let me put a little border here. You start off with the 20 degrees, and then you add, you're going to go 360 degrees times whatever k is over your n. So 360 degrees divided by 3, that's your n, that's going to give you 120 degrees. So essentially, all I have to do is add 120 degrees to each previous solution, okay? Or you could just key in the number each time. It's really up to you. So in the first case, it's going to be times 1, so it's just 120 degrees. So it's the previous guy, 20 degrees plus 120 degrees. That's going to give you 140 degrees. So this is 140 degrees plus I times the sine of 140 degrees. So again, all I have to do now, I don't have to go through the whole formula again. You can if you want to, but you're just adding 120 degrees. So 140 degrees plus 120 degrees, that's going to be 260 degrees. Plus I times the sine of 260 degrees. All right, so these are my solutions for x. Again, in each case, I could cube this number, and I would get back to this 4 plus 4i times square root of 3. Now, if we want to graph this guy, again, the magnitude of each vector, or the absolute value of the complex number, is going to be 2. So you're going to sketch a little circle. Let's look at that here. And basically, the radius is going to be 2, right? So the center's at the origin, the radius is 2. So each vector is going to touch that circle at the tip. And then you can basically say, okay, well, this vector right here, it's going to be a direction angle of 20 degrees, and then they're all spaced from there 120 degrees apart. So you go another 120 degrees, you get to this angle, which is 140 degrees. You go another 120 degrees, you get to this angle, which is 260 degrees. So this is how you could sketch your solutions.